Welcome friends in a new lecture series of electromagnetic field theory. Here we are going to discuss the basic concepts behind electromagnetic field theory. So the first is definition of electromagnetics. In a simple language, we can say that electromagnetics is a branch of physics or electrical engineering in which electric and magnetic phenomena are studied. So here we first talk about electrostatics and then we talk about magnetostatics. And the combined effect is called electromagnetic effect. Also, we can say that electrostatic is the study of interactions between electrical charge at rest and in motion. This electromagnetic effect is used for many applications, such as electric machines, satellite communication, microwave, antenna, nuclear research, fiber optics, electromagnetic interference, electromechanical energy conversion, and many more. And the devices corresponding to these applications are called electromagnetic devices. For example, transformers, electric relays, radio, TV, telephones, electric motors, transmission line, waveguides, etc. And as far as the designing is concerned, we require a thorough knowledge of laws and principles of electromagnetics. Before starting laws and principles of electromagnetics, we first go through vector algebra. The first point is, any vector has its own unit vector. As we know that vector is the quantity which has magnitude as well as direction. So any vector A having magnitude mod of A vector and its direction is represented by its unit vector, and it is denoted by small a vector. So the unit vector of vector A is equals to A vector upon magnitude of A vector. Next concept is vector addition. For this, we consider two vectors, vector A and vector B. And for addition of these two vectors, there are two rules. First is parallelogram rule and the second one is called head to tail rule. In parallelogram rule, the tails of both vectors are joined together and make a parallelogram. And the resultant of these two vectors is represented by the diagonal of the parallelogram and it is denoted by C vector. So C vector is equals to vector A plus vector B. And in case of head to tail rule, the head of vector A is joined with the tail of vector B. And the resultant addition is represented by vector C that is drawn from tail of vector A to head of vector B. And this is called head to tail rule. So here also C vector equals to A vector plus B vector. Next concept is vector subtraction. Here also we consider two vectors, vector A and vector B. For the subtraction of these two vectors, that is vector A minus vector B, we join the tails of these two vectors. Now for subtraction, we draw opposite of vector B, that is called minus B vector, and using parallelogram addition rule. And here the resultant of vector A and minus vector B is D vector. And D vector is simply the addition of A vector plus minus B vector. That is A vector minus B vector. And it is called vector subtraction. Also, when we require B vector minus A vector, so in this case we draw opposite of vector A, that is minus vector A. And similarly, we draw a parallelogram corresponding to minus A vector and B vector. And the resultant of these two vectors is vector E, and it is B vector minus A vector. Next is position vector. To understand this, we consider XYZ axis, that is called orthogonal system. Here all the three axes are perpendicular to each other. And to represent this type of system, we consider a right hand thumb rule. Here, when we move X toward Y, that represent a curl of a finger, then thumb corresponding to Z direction. So to represent position vector, we consider XYZ axis with center as origin and its coordinates are 0, 0, 0. Now, for position vector, we consider any point P on this three-dimensional space with coordinates X, Y and Z. Now, we join point P with respect to origin. And the vector formed after joining is called position vector, that is denoted by small r vector. Here the position vector can be represented mathematically as final point minus initial point. Here the final point is the coordinate of point P, that is XYZ, and the initial point is the coordinates of origin. So from here we represent position vector small r having coordinates X, Y and Z. And in terms of unit vectors, we consider unit vector X along X-axis, unit vector Y along Y-axis and unit vector Z along Z-axis. These unit vectors having magnitude of unity. So the position vector small r is equals to X unit vector X plus Y unit vector Y plus Z unit vector Z. Now, after representing a position vector small r, this position vector also having its own unit vector, that is denoted by small a suffix small r, and it is a ratio of small r vector upon magnitude of small r vector. And the magnitude of r vector is under root of x square plus y square plus z square. Next concept is distance vector. Here also we consider XYZ coordinate axis, and on this three-dimensional space we consider 2 points P and Q. The coordinates of point P is x1, y1, z1 and point Q having coordinates x2, y2, z2. And here we have to determine the distance vector between point P and point Q. For this, we first draw a position vector with respect to origin. So for point P, the position vector is P vector, and for point Q, the position vector is vector Q. Now, there are two ways to draw distance vector. It may be from point P to point Q or vice versa. So here we first consider distance vector drawn from point P to point Q. That is denoted by D1 vector. This distance vector D1 having its own unit vector represented by small a D1 vector, and it's directed from point P to point Q. Also we know that position vectors P vector and Q vector is always directed from origin towards their corresponding points. So from here we use vector addition. Here we see that vector addition can be possible when we add vector P plus vector D and the resultant is vector Q. And in order to determine distance vector D1, it is equals to Q vector minus P vector. As the coordinates of Q vector is Q2, Y2, Z2 and coordinates of point P is X1, Y1, Z1. So the distance vector D1 having coordinates X2 minus X1, Y2 minus Y1 and Z2 minus Z1. And in terms of unit vectors along X, Y and Z axis, distance vector D1 is equals to X2 minus X1 unit vector X plus Y2 minus Y1 unit vector Y plus Z2 minus Z1 unit vector Z. Here also this distance vector having its own unit vector denoted by small a vector. and it is equals to d1 vector upon magnitude of d1 vector, and it is directed from point P to point Q. Similarly, we can also represent distance vector from point Q to point P, and for this case we represent d2 vector. Here also we use vector addition, but in this case q vector plus d2 vector is equals to p1 vector, and the distance vector d2 vector is equals to p vector minus q vector. Now using corresponding coordinates of point P and Q, d2 vector is equals to x1 minus x2, comma y1 minus y2 and z1 minus z2 as its coordinates. And in terms of unit vectors corresponding to x, y and z axis, d2 vector equals to x1 minus x2 unit vector x plus y1 minus y2 unit vector y plus z1 minus z2 unit vector z. This distance vector d2 having its own unit vector denoted by small a suffix d2, and it is a ratio of d2 vector upon magnitude of d2 vector. Next is vector multiplication. Here we discuss multiplication of two vectors, and the methods are dot product and cross product. So first we discuss dot product. It is also called scalar product because the dot product of a vector and b vector results a scalar, and the dot product is represented by a dot between two vectors. So the scalar product represented by a vector dot b vector, and it is equals to product of the magnitude of a vector and b vector and cosine of the angle theta between vector a and vector b, and it is equals to a into b cos theta. And here in dot product the first vector is a vector, so we take cos theta with magnitude of a vector, and this a cos theta is called projection of a vector on b vector, that is shown in figure. Here we draw a perpendicular projection of a vector onto vector b, and the projection, that is a cos theta, is a magnitude. So the result of dot product is scalar. Similarly, we can also determine b vector dot a vector, and it is equals to product of the magnitude of b vector, a vector and cosine of the angle theta between these two vectors, and b vector dot a vector is equals to b a cos theta. Here the first vector is b vector, so we take cos theta with b, that is magnitude of b vector, and this b cos theta is the projection of b vector onto a vector, that is perpendicular projection. In dot product we note some points. The dot product obey commutative law, that is a vector dot b vector is equal to b vector dot a vector. Also the dot product obeys distributed law, that is a vector dot vector b plus vector c equals to a vector dot b vector plus a vector dot c vector. And the third most important point is the dot product of same vector is equals to square of the magnitude of that vector, that is a vector dot a vector equals to a square, because here the angle theta between the same vector is 0, so cos 0 is 1. So in this case a vector dot a vector is a square. And in terms of unit vectors along x-axis, y-axis and z-axis, that is the orthogonal system, the dot product of unit vector x, unit vector y, or unit vector y, unit vector z, or unit vector z, unit vector x is always 0, because the angle between corresponding unit vectors are 90 degrees. So cos 90 degree is equals to 0. Similarly, unit vector x dot unit vector x or unit vector y dot unit vector y or unit vector z dot unit vector z is always equals to 1, because the angle between the same unit vectors is 0, or we can say that cos 0 equals to 1. Next method of vector multiplication is cross product. It is also called vector product because here the result is vector quantity and the cross product is obtained using right hand thumb rule. To understand the cross product, we consider two vectors, vector A, vector B, on a plane joined by their tail. Now, in order to determine vector A cross vector B, here the first vector is vector A, so we move vector A towards vector B by some angle theta. That is represented by the curl of the finger. And the thumb represents cross product, that is A cross B vector. And the direction of this cross product is normal to this plane. So the cross product A cross B vector is equals to product of the magnitude of vector A, vector B and sine of the angle theta between these two vectors. This cross product having a direction, that is normal direction to the plane, and can be determined using right hand thumb rule. Similarly, we can also find vector B cross vector A. In this case, the first vector is vector B. So we move vector B towards vector A using right hand thumb rule. And in this case, the direction of the thumb is downward. That represent B cross A vector. So the cross product B cross A vector equals to product of the magnitude of B vector, A vector and sine of the angle theta between these two vectors, and the direction is minus unit vector n, that is normal unit vector in opposite direction. So finally, A cross B vector equals to AB sine theta unit normal vector, and B cross A is equals to minus BA sine theta unit vector n. Cross product can also be determined using matrix. Here we consider vector A and vector B having xyz coordinates. So here we consider vector A having component ax, ay, az correspond to xyz axis. Similarly, vector B having component bx, by, bz. Now the first is A cross B vector and the matrix is, here the first row is for unit vectors, that is unit vector x, unit vector y, unit vector z. And the second row corresponds to the component of vector A and the third row is for components of vector B. Similarly, for B cross A matrix, the first row is for unit vectors. Here the second row is for components of B vector, because here the first vector is B vector. And the third row having components of A vector. So in this way we can use matrix in order to find cross product. Next we are going to determine cross product of unit vectors. For this we again use a right hand thumb rule with thumb pointing in and the curl of the finger represent cross product, and that is clockwise direction. So unit vector x cross unit vector y is unit vector z. Because the magnitude of unit vectors is 1 and since this is an orthogonal system, the angle between unit vectors are 90 degree. So sine 90 degree is equals to 1. Also unit vector y cross unit vector z equals to unit vector x. And unit vector z cross unit vector x equals to unit vector y. This cross product can also be applicable in opposite direction, that is anti-clockwise direction. But here the direction of the thumb is outside the paper. So unit vector y cross unit vector x equals to minus of unit vector z. Similarly, unit vector z cross unit vector y equals to minus unit vector x, and unit vector x cross unit vector z equals to minus unit vector y. So the multiplication of two vectors require dot product and cross product. Next is scalar triple product. Here we can multiply three vectors and the result is scalar, so it is called scalar triple product. Scalar triple product is a combination of dot product and cross product. To understand this, we consider three vectors, vector A, vector B, vector C. So the combination of scalar triple product is, when we consider vector A as a first vector, so it is with dot product, and the second or third one is for cross product. So the first is A vector dot B cross C vector. Similarly, when we take B vector as a first one, then combination becomes B vector dot C cross A vector. And similarly, when we take C vector as a first one, then triple product is C vector dot A cross B vector. So in this way, we can represent scalar triple product. And we know that the cross product of two vectors results a vector. And since, for example, A vector is a vector, B cross C vector is also vector, and the dot product of two vectors results a scalar. So in this way, the result is scalar, so it is called scalar triple product. Scalar triple product can also be represented in matrix form. Here, all the three vectors, vector A, vector B, vector C, having x, y, z components. So the matrix is like this. Here the first row having a component of vector A, second row having a component of vector B, and third row corresponding to the component of vector C. Now the next is vector triple product. Here also we can multiply three vectors, but the result of this multiplication is vector quantity. So here we again consider three vectors, vector A, vector B, and vector C, and to represent vector triple product, we use hint, that is A cross B cross C is equals to B vector into A dot C vector minus C vector into A dot B vector. So here the hint is BAC minus CAB. And we know that the dot product of two vector is scalar quantity. So here the first term is B vector into A vector dot C vector. The result of dot vector is scalar, and the multiplication of vector and scalar is also a vector. So the first term is a vector quantity, and similarly the second one is also the vector. And the difference between the two vectors is also a vector. So the result of vector triple product is a vector quantity. That's why it is called vector triple product. Now we note a point. When we take dot product of two vectors, that is A vector dot B vector, then we can write C vector into A vector dot B vector equals to A vector dot B vector into C vector. But A vector dot B vector into C vector is not equals to A vector into B vector dot C vector. Here the dot product of vectors are different one, so this is not equal. The equal is only when the dot product is of same vector.